Let's begin. So I'm Mike Douglas, and I'm going to tell you something about machine learning and language. So, assuming that the computer cooperates. There we go. Okay, so language is obviously something we're all familiar with and interested in, and people have studied it for a very long time. And it's amazing how much even ancient people knew about language. Of course, it's important, for many things, to make society run, to demonstrate one's ability in various ways, and so people were motivated. And many people study language, but you can still very reasonably argue that we don't understand language, and this is one of the big questions as to what makes us human. How does the brain work? So if you try to distinguish humans from the other animals, language is certainly the primary way that you would distinguish them, and the primary ingredient in intelligence. And then a problem with this question is, what does it mean to understand language? I mean, we all understand it in the sense we all understand what each other was saying, but then if you can't make a theory, well, maybe you don't understand it, but if you can't make a machine do it, this is a more modern criterion, then you certainly don't fully understand it. So Feynman said famously that if I can't create something, I don't understand it. And so can we create a computer that uses language in some way? And the answer is, at this point, unclear. I would not say that computers and the programs that will demonstrate understand language, but it's very interesting what it can do. Okay, so how are we going to do this? And the obvious idea that might come to mind is to make a robot and put it in an environment like a human, a small child learning language. And of course, there's many challenges in doing that, and we wouldn't treat the robot the same way we treat a baby anyways. But still, the fact that small children learn language without being taught very explicitly. You might correct them if they make a mistake. You might show them things, but you certainly don't try to teach them the rules of grammar. And it's really very unsystematic the way that people are taught language, but they just absorb it. They just pick it up without really any difficulty. And so, well, what are they doing when they do that? That's another excellent question. They're not just listening. They can obviously ask questions once they get to a certain point, but a lot of the learning, certainly the foundations, are before they ask questions. A baby responds, and you can tell when a baby is paying attention to something, when it is surprised by something, and you can see that even if it's a year old, it doesn't understand, but it definitely is picking up a lot of the meaning in language, and it's not asking any questions, obviously. So there's clearly a great deal that you can get just by listening and observing the world around you. Okay, and there's lots of things to observe. You might think that to learn a word, you should see the object and associate it to the word, but it's also true that language in itself has a lot of structure, and that if you say a word very often with other words, then it's a good guess that those words have something to do with each other. And if you have enough language in front of you, maybe you can infer things about not just the relations between the words, but something about what they mean. Obvious cases like stating a fact. But again, people don't tell lots of facts to their children. The children just kind of pick it up from the language and what's around them. So could we program a computer to do that? Okay, well, that certainly saves a lot of the trouble of making this robot and all these other things. And in particular, there's a huge amount of text on the internet these days, and computer can process it very fast. So if you think about it, and this is an easy calculation to do, take the number of seconds in a year, it's about 20 million, And you figure, well, you could hear or read maybe 10 million words in a year. So even if you live to be very old, you'll encounter at most a billion separate words. And the computer can read a billion words very quickly, and it can even process them and try to make these correlations and analysis or whatever it is very quickly. So maybe just by turning it loose on the internet with the right programs, we can get something that understands something about language. And people have had some success with that. And so I'll describe some of the basic ideas, and then we'll make this demonstration. Okay, so the simplest and definitely the program that I'm going to show you is an example of a language model, or to be more precise, a statistical language model, because what the basic idea is that we just forget from the start, what does anything mean? It sounds crazy. How can you understand language without knowing what the words mean? But you can go surprisingly far, ignoring, at least as the inputs, any discussion of what things mean, and just saying, well, this is associated to that, this is correlated to that. So questions treating the language statistically. And so what is a statistical language model? Well, you break down whatever the language is into some sort of units, and you have a choice as to what you think the units are. You can get different models, and then you just compute the statistics. How often do the units appear? How often do the units appear in relation to other units, and so forth? And it has to be a generative model, and a generative model means that it's not just the statistics. There's some way of then producing things with the probabilities that the model predicts. I mean, there are other models, but they wouldn't be so useful for what we're trying to do, which is to make the computer make language. So we'll talk, and there'll be certain points where just giving probabilities isn't enough. We'll have to say, how do you use the probabilities? Okay, so to start with a really simple example that probably you've all seen, you can look at the letters in English, and of course some letters are more common than others, and the most common letter is E, and the least common letter is Z. And it's very easy to just go through a text and count the letters and see what fraction of the letters are, E, T, A, and so forth. And this is a graph, so E's are about 13% of the time, all the way down to Z's, which are negligible. And then this gets used for various things. For example, when the game Scrabble was designed, it's clearly better to reward people for the rare letters, which are hard to use. And so a Z is worth, and a Q is worth 10 points, and an E is worth 1. So in some sense, I mean, this is perhaps the simplest language model. We've broken down the text into letters, and we've statistically characterized how often does each letter appear. Okay, so what can we do with that? Well, of course, we could generate text by that model. We could just pick letters according to those probabilities, and we would get things like this, A, P, R, N, so forth. It's not English, obviously. It has properties like English, okay? And then you can even see words in it. You got thee, you got we, you got now, and so forth. I mean, total chance, obviously, but a sort of a meaningful total chance, because if you just took the letters all with the same probability, you would not see words. You would see very, very few words, and then now we're seeing words. So we have captured something about English, but only the tiniest bit. Okay, so how do we do better than that? Well, obviously, letters are not just independent choices, and the letters satisfy many patterns, and then we can try to describe those patterns statistically. And so the most obvious would be something like, if you see a Q in English, there's always going to be a U after it. And so you can start with definite rules like that, which are always true, but you won't get very far, because especially if you've in English spelling, it's very clear. The rules are rules made to be broken. There are just as many exceptions as there are rules. And so you have to be a little more clever than that, but you can find statistical rules. You can say that this letter usually goes along with that letter, and then of course you can quantify that and say, well, what fraction of the time does this letter follow that letter? Okay, so people, of course, tabulate all these things. And the most common two-letter sequence in English is TH. And, well, what could you do with that? Well, many of you have probably taken a course or read a book on cryptography, so trying to break codes. So a typical simple code would be to substitute. So the simplest would be just, you take every letter and you add 3, you go 3 more letters down, and then that's very, very easy to break. And then the next would be to have a table. A goes to a G, B goes to M, and so forth. And so that's the kind of code that you would learn to break in one of these courses. And so statistics is really the most effective way to do that. So a simple thing you could do with a computer is take all the bigrams, all the pairs of letters, find out what's the most common pair, then probably that maps back into the most common bigram in English, which is TH. Not definitely, but probably. And so you have to be able to use this kind of statistical information. Okay, so that was all to illustrate, what is a language model with models that you've probably already seen and played with a bit. But letters obviously are too low a level. Letters don't individually have meaning. So if we want the computer to get any sense of meaning, we're better off working with words. So let's base the model on words. So now we're going to talk about the probability of particular words in English, the probability of pairs of words, that kind of thing. And of course, the idea is the same. There are many more words, but if you want to estimate the probability of words, you take a huge collection of text, which people usually call a corpus in this business, the Latin for body. And then you count all the words, you make a big table, and so here's a classic sentence. There's got 2 copies of the word would, it's got 1 copy of the word how, and so forth, and it's got 13 words total, and then we can make the simple estimate that if we were really just interested in reading that sentence over and over, we could estimate the probability that we're going to see the word would as 2 divided by 13. It's just the number of times it appeared in that sentence relative to the total number of words. And so that's a language model too. Of course, if we just base it on that sentence, it's a very, very simple language model. But if we base it on billions of words, say, coming out of the internet, we already can get something out of that. That's some sort of a language model. And of course, people have done that. So this is about 1 billion words fed into counting and producing such a model. And this came off of Wikipedia, basically. So this is coming out of a library of 24,000 non-copyrighted books, which I think has expanded to about 50,000. And so what are the most common words? Well, for some reason, the most common words start with A. This is actually an order, decreasing order of frequency. So the most common word is A, then about, then after. It's strange that things start with A, then things start with B, then things start with C. But I have no idea why that should be. But, well, it really cannot be. I think these must be just the top 100 organized alphabetically without pertaining to, although the way they described it was not that. But this has to be in alphabetical order, clearly. So anyways, we've got this list of words, and we could try to use that as a language model. We could say, let's pick out words with whatever probabilities this thing, this list gives. Okay, so one interesting aspect of that already is that the words and their frequencies are going to depend on what kind of input you give it. So this was all these classic books. So people also did it for TV and movie scripts. Okay, there's not as many as those. So they had 29 million words that went into that. And some things obviously stand out, like okay. This is a pretty common word in a TV script, and it's not there in these 100-year-old books. Yeah. People say yeah, but they don't write yeah in classic novels. So there's some differences, and then already you could try to say things about, what are the differences between, classic novels and TV scripts by just looking at these word frequencies and language models. And people sometimes use this kind of data to say, well, who wrote, is this really a lost play of Shakespeare that somebody found in their attic? And if the word frequencies look like this, probably not, and if they look like this, well, it's a little more likely, who knows? And okay, so then what do we do with such a language model? Well, the basic thing you do with the model is you sample from it. You try to make text that satisfies whatever are the rules of the model. So in this case, we sample according to the probability. The most likely words come up more often. The less likely words come up less often. And we get stuff like this. So this was off of, in fact, somebody who was using this to put the kind of nonsense text in a web page. If you're like illustrating, here's my web page maker, and then you read the text and it's all this kind of nonsense. Luckily, friends do, ashamed, da da da. And anyways, as they say, it looks better than just having ZZQW and so forth, like on my previous slide. We've definitely taken a step up from that, but we haven't taken a very big step, clearly. Okay. So what's the next step? Okay, well, the thing that people did a lot in the past, and without a computer, this is pretty much the best you can do, of course, is to try to learn the rules of the language and try to use the rules, okay? And so in particular, there was this game that, when I was a kid, and I think it still exists as an app called Mad Libs, where they would have little booklets with sentences with some of the words taken out with blanks. And then you're supposed to fill in the blanks. You ask somebody, what's an exclamation? What's an adverb? They give it back. Wow. Quickly. What's a noun? A cat. And then you would fill it in, and then you would get these sentences which were supposed to provoke much hilarity. So you can see that these kind of games have advanced a lot since I was growing up. But in any case, the point I want to make with it is not that this is a great game. It's that you have to give the part of speech. You have to fill this guy with an adverb. You have to fill this guy with a noun and so forth. And then you're going to get a sentence. And if you don't do that, you're just going to get something, well, better than this, but not much. So you can try to use the rules of English to try, or your language, to try to improve your model. And so that's definitely a good thing to do, but there's actually a much more easy and systematic thing, and it's much easier for the computer to do, which is instead of just looking at the statistics of single words, to look at groups of words, the same way we talked about with the groups of letters and the bigrams. And so one uses the same word gram, for any linguistic unit. And so this is referred to as an n-gram model. Okay, where n could be 2 if it's a 2 or a bigram model, n could be 3, in principle n could be a large number. And it's the same starting point to say that, we're going to take pairs of successive words, how much would, ... and just make a table. How many times does each pair or bigram appear in our corpus? So it's very, very straightforward. No problem programming a computer to do that. Okay, and so then obviously we would follow the same kind of rule to say, there are 12 pairs of successive words, and so we might say that the probability of this is 2 over 12. But then this is where the slightly tricky point comes in, which is that, of course, when I say how much and I say much would, those are not independent choices, because once I've said how much, this word has to already be much. And so I can't just put any bigram there. I have to put something that starts with much. Okay, so I can't just sample the probabilities. I can't just pick the things according to the probabilities that I would get out of this. Okay, so there is a solution to that, and this is maybe one of the useful things, if you haven't already seen it, you will get from this lecture, which is that there's a very general solution that people use all the time in all these things called a Markov chain. Okay, and what the Markov chain is to be a little bit more systematic and say, in this case, it's kind of obvious. Well, since we've already picked how much at this point, we know the next bigram has to start with a much. We're going to just focus on the guys that start with much and look at the probabilities of what's the next word given that the first word is much. Okay, so that's what we do, and that's what's called a conditional probability. And since it gets used all the time, there is a notation for it, which is instead of just P of word, P of whatever new thing we're talking about happening, bar, and then the condition, whatever the old thing is that we are saying already happened. Okay, so here we're saying, given that the last word was much, the probability of getting a word W is denoted P word much with the bar. And then it just obeys the laws of probability. So given that we've stated the condition, the sum of all the possibilities has to be a 1. There's supposed to be a P there, of course. And then that's it. That's the bigram conditional probabilities. And that's what we need to sample from this. And they're not any harder to work out than the naive ones. Just when we count the bigrams, we have to not divide by all the number of bigrams, which was this naive idea of probability. We divide by the number of times that first word appeared. Okay, so if you think about it, then this is saying, well, every time you see word W0, there might be 3 times that the next, this particular word appears, 7 times this particular word appears, but we should only take the fraction out of the things that already had the word 0. Okay, so a little, think about it a little bit, maybe play with an example on your own, and this formula will start to become clear. And of course, it does satisfy this property that if you sum up over the W1s with a fixed W0, they add up to 1. So that was the main thing, to say that it's actually a probability. And so then, if you got that, then it's straightforward. So we'll say we start with a word. We'll just pick a word how. Okay. Then we know these guys, so we pick the next word W1 with these probabilities. And now we know W1, so now we're going to pick word 2, W2, with these probabilities and so on. So that gives exactly the information that you need to sequence through the text and pick each word successively. Okay, so that's a Markov chain. Okay, and then that idea generalizes. That idea, the basic point is that you always kind of saying the computer keeps track of something, like the last word, or maybe it's the last 2 words, and then the probability of its next choice can only depend on that something it kept track of. It can't keep track of anything else, and that's going to go in order. And then, if you think about it, you'll see that a lot of what we said for the bigram, you can generalize very quickly to the other grams. So like a trigram, a 3-word thing, what we would really want to say is, suppose we already had these 2 words, like how much, then we have to choose the next word, and it can depend only on those last 2 words, and then we would estimate by counting trigrams and normalizing it this way. Okay, so then I have a demonstration, but I decided this guy would take a little more time than I want. So I'm just going to show you a demonstration out of a textbook. And after lecture, we can come back and look at this demonstration for people who like. So this would be sampled. So we've counted up all the words in Shakespeare, basically. And then we're comparing. This is just going according to the individual word probabilities. To him, swallowed, confess here both, which of save on trail for I our device. So you can say it like a Shakespearean actor, but it doesn't sound very much like Shakespeare. And then the 2-gram model, why dost stand forth thy canopy forsooth? He is this palpable hit, the King Henry. So it's getting a little better, and the 3-gram is better still. And the 4-gram, I don't know, King Henry, what? I will go seek the traitor Gloucester, exeunt some of the watch. A great banquet served in. So that one, the sentences are starting to make sense. Of course, it kind of skips back and forth between different topics. But already the 4-gram, you can start to see something like English there. Not with a very clear meaning, to be sure, but at least in terms of the grammar, the vocabulary choices making at least some sense and so forth. And so this might start to convince you that, well, this language model is Yeah, it seems kind of crazy at first, but it is getting something about English. Okay, so that would be generating text. Okay, so now we could say, well, okay, that's very good, but I want my computer to answer a question for me. How do I ask it a question? And you can actually do it using this in principle. Okay, and so you would again use this idea of conditional probability. Okay, so suppose as an example, you ask me, what is the capital of France? And of course, I would say Paris, or maybe I'll say, well, the capital is Paris. I might say something else. And so then, if the language model is modeling a person who knows that, then that could be reflected in these probabilities. What is the capital of France? That was the condition. That was the text that came before. And then what's the next word going to be? Well, probably it's going to be Paris because that's the answer. So we're going to give that 95% probability. Okay, but then he might have said something like, the capital is Paris, or something. So maybe we'll say has 4% probability, or maybe you'll say, what do you want to know for that for? What do they teach you in school, anyways? And so maybe what is like 0.5%, or so you could list all the possibilities, but it's clear that if you're describing the probabilities of a text in a dialogue, that this is going to be very high up there, and that you could feed in the question as this condition in the conditional probability. And so if the fact is there in the text, then maybe the computer could learn it just through this statistics. So that would be like, I don't know, it would be incredible, I would say, without really, see, this would be a way of getting the computer to use language, answer questions, without really answering any of those deep questions that we talked about on the first slide. We would still have no idea how language worked. We just turned it into this problem of statistics, and it did it. So that would be kind of weird. Okay, so but who knows? Okay, so I've 10 minutes, I think, until we have 10 minutes for the demonstration. So interesting question. If people want to ask questions or say what they think about this idea, we could discuss a little bit, or else I'll move on. I don't know. This is the basic idea. This is the basic idea. Okay. Does this kind of make some sense? Do people have questions about it? Yeah.
So how could you apply the same sort of technique for more open-ended questions? So for example, ask for the capital of France has a specific direct answer.
Right. So say it again. So we asked a question and.
How would it be possible to use the same techniques for more open-ended questions?
Oh, more open-ended. Well, obviously, as a technique, we can feed in any question we want here, because we don't know what we're going to get out. It's just whatever the properties of the language are. So I agree. We would, a version of that question would be, how do we know that these answers have anything to do with the meaning of the question? And the answer would be, we have no clue. It's just the statistics of language. So, yeah, that's only one problem with this idea. Okay, so there's another more technical problem, although a very deep problem as well, which is that once you start using these n-grams, you start to, everything becomes rare. Okay, so there were only, let's say there's many fewer than 10,000 common words. 10,000 words will get you very far, but already there would be 10 to the 8 bigrams, 10 to the 12 trigrams, and we're not going to get text with 10 to the 12, a trillion words in it. So most of the three-word combinations won't appear just because there's not enough text, just because there's so many possibilities, and any given text is finite. And even three-word combinations that are very reasonable, that if an elephant is stepping on a banana, you might want to say that, even though there's nothing about that in your text. So this is the combinatorial explosion, which is a very, very common feature of kind of naive attempts to do things in computer science and AI. And so it's just not going to work in the form that we just said it. Okay, so what do we do about that? And so one idea is to say, well, it's kind of stupid to say that every word is just a word in itself with no relation to the other words. Obviously, words have lots of relations between them. They have a part of speech. There's a classification. A cat is a mammal is an animal, and so forth. And there's just lots of things you can say. And of course, it's very complicated to think about all the things you might say about a word. But somehow that's what the models I mean, it's not totally missing it. If you could give it, zillions and zillions of words, it might learn all that stuff. But we don't have zillions of words. We only have billions of words, and it's not going to learn all that stuff. Okay, so that's kind of the next step in this discussion. Is there's this thing called a word embedding. Okay, so what's a word embedding? So we're going to not work with the original words. We're going to assign numbers to the words, which are longer numbers. So like a given word might have 500 numbers associated to it. And here's an example that you can get off the web. Somebody worked one of these out. So there's actually 300 numbers in this embedding associated to each word. And they're just like they're random looking numbers. Fawn is 0.089, 0.121. And it's a 300 dimensional space, if you're familiar with that terminology. But it just means every word has 300 numbers associated to it. And that information is supposed to be better for the computer. It's supposed to have more information in it than the original word. Okay, and why do we say that? Okay, well, the numbers are a little hard to visualize, and so you could make a heat map. Okay, so this is word, and then this is, I don't know the same numbers, but another word embedding that I think it's the same numbers even, that we've taken the large positive numbers and made them red. We've taken the very negative numbers and made them blue, and then there's a range in between. And so now you can kind of visualize, well, all the words have this in common, at least all the words we've shown here. We don't know what that means, but all these top words seem to have this in common, and water less so. Well, maybe this is has to do with a word for a person, and then this is not a person. Maybe this is noun. You have to look at some other words to figure it out. I mean, if you went through all this stuff, you might be able to see, what do these different numbers mean. But we're just going to grant that this captures relations between words. Okay, this is a kind of a more useful input for the computer. Okay, so how do you find this sort of thing? Well, that's interesting and a little technical. Just to give the basic idea, this is now where we get into the machine learning. And what we say is we're going to come back to sentences. We're going to have the same kind of corpus of text. And the basic kind of problem is going to be to predict a missing word. So like well, I'll just come back to, it could be any place on my slide because it's all sentences. Let's suppose we take this guy, and you could do two things. You could say, let's rub that word out. Let's look at the numbers associated to all these other words and say, can we predict that word? Okay, and then, the answer is, well, if the numbers were really related, maybe you could predict this. You may add up all these numbers and then find the number closest to that, and that would be that word. Okay, so that would be a way of using numbers to predict words. Or you could go the other way around, which is actually turns out to work better. You could say, given the number for this word, can we predict those words? What other numbers or vectors of numbers are close to that one? Maybe these ones are close to it. And then there's this training process that says that once we've got the task, predict word, then we define some function that says, well, how good is it doing at that? Is it predicting the words poorly or well? And then we program the computer to look at examples, predict the word supposed to be water, it got cat, that's not very good. So these are the numbers that were responsible for the mistake. Let's change them a bit so that it's less likely to make that mistake next time. These ones weren't involved, so let's not change those. Maybe they had to do with other words. Okay, so that's the training process. And I believe other lecturers, other labs at this school will talk about examples of this, where simpler, where you can get the idea. But then the idea just kind of scales up to this. So this idea of training is very important, and then eventually you can turn a corpus of text into these numbers. Okay, so an amusing thing about these, which I must mention, is that the simplest thing once you've got numbers is you can add and subtract them, and these actual vectors satisfy approximate equations. Okay, so if you look at like king, girl, boy, man, woman, you can write out the numbers here, and you could take equations like king minus man plus woman. So 300 numbers minus 300 numbers plus 300 numbers, you get another 300 numbers. And it won't be any of the things in the list, but now you can say, what's the closest one in the list? What's the word that has a vector closest to that one? And it turns out to be queen. Okay, so that's a real demonstration that these vectors are capturing something about the meaning of the words. They're not just random numbers. Okay. Okay, so that's a crucial step, the word embedding. And then you have to start shifting over. So this, you want to do something like the Markov chain that picks words in according to probabilities, but now you have to translate it all into these vectors. And so again, these are kind of the basic machine learning models that people use these days. So the task might be put in a word, and we're going to try to put out a word, and we're going to say, you might try to predict the next word. Okay, that's a very typical thing. Given that you got up to here, let's predict the next word in the text. Or for each word, let's predict what word comes after that. And of course, it's not just going to depend on the word you put in, it's going to depend on all the other words in the sentence. And the recurrent neural network is a way of making its prediction depend. It depends most on the word you just saw, but then it also depends on all the words before. And so there's a set of equations, I'll write down a little bit of that, which involve matrices of numbers acting on these vectors. So X is one of these 300 component vectors we talked about. You multiply by a matrix. You might add it into something that you've got. You might add it into, in particular, the state is a vector that is already sitting there. Okay, so this is like a single unit of calculation, but then when you apply it to one word, the next word, the next word, the next word, the data kind of feeds through according to these arrows. And then finally, by applying these matrices, you get the prediction, what's the next word, and you get the new state, the thing which is like in the Markov chain, saying, what did I see before that will condition, will help me determine, the probabilities for what's coming next. And then you would train it to make these correct predictions, to say, well, if I saw up to here, am I good at predicting what comes next? And usually the answer will be, no, not very good. Obviously, it's very rare that you can literally predict the next word, but you could have a list of probabilities to say, well, probably it's this word, maybe it's that word, maybe it's that word, and then you could judge, well, is that a reasonably good set of probabilities? Is that a good model for this prediction? And then train it based on that. Okay, so that's the kind of model that is now getting used. And this is a little bit more mathematical detail. I'll probably, if you like afterwards, we can come back to that slide. And then that dates back, I mean, the idea dates back a while, but really using it for these language models dates back about 10 years. And now here's the thing which people discovered 2 years ago, which led to this GPT-2 and stuff, and it's something called attention. And so the problem with the thing I just said, of course I didn't explain it that well, but I can tell you, and you can maybe even guess what the problem is, which is that when you're predicting a word, it's not true that it depends mostly on the word you just saw. It might depend on a word way back in the sentence. It might depend on a word you didn't even hear yet, ahead of you in the sentence and so forth. And this model is only good if it depends mostly on the word you just saw. Okay, but you need to be more flexible and allow things to depend on any of the words, at least in a sentence. And so the way that is done, the kind of model people uses something called attention. And I've just given kind of a schematic diagram. So it's got the various words in the sentence, and now it's using numbers not just for to represent each word. It's going to process those numbers first to decide which word is most relevant to predicting, this word. So I'm trying to predict, vectors, and so maybe word is relevant, maybe matrix, seems associated to vector. That seems very relevant. So the computer really should realize that this is an important word to look at if I'm trying to predict that word. And so it first does a stage of processing where it takes these word vectors and kind of looks at, again, it has various matrices that it's learned, and it uses those to look at the vectors for each word in the sentence and say, well, here's a relevant one. Here's probably not a relevant one. And then it focuses on the relevant ones and adds up according to the weight. If this one's important, it will add up that vector with a high coefficient. If it's not important, it might leave it out or add it with a low coefficient. And then it does the kind of thing we talked about on the other slide to make a prediction. And so then you can soup that up. And then the thing that I'm about to show you is a version of using that called a transformer network. And so here's a diagram of the sort of thing, which looks much more complicated than what I just showed you, and it's more complicated, but it's not infinitely more complicated. You know, the programs before this, you know, before people started doing it this way, just were incredibly complicated and didn't do such a great job. And this, at least, you know, you could learn. You know, this is not it's more complicated than what I showed you, but as these things go, as a model of the English language, it's not really that complicated. Okay, and it's built out of these ideas. So we've got attention, we've got two sets of things, partly because this is a more general thing that could also do like translation of one language into another language and so forth. But we'll just look at how it generates. Okay, so that's the slides. Are there questions, or should I just go on to this demonstration? Or I can go on and then you can ask questions. Yeah.
So when it says outputs shifted right, does
Yeah.
that mean that it's feeding its outputs back from the last round?
Yeah, that's right. So this is this idea that we're going to, we might, especially when you're doing translation, this is a useful thing, you know, that you might base the output sentence. You're generating a sentence, you know. So the basic thing of translation is you're generating a new sentence, and you're trying to predict the next word given the previous words. But now, obviously, not just generating any sentence. You have to generate one which is meaning the same thing as the first one, and then that's where that gets fed in. Yeah.
So which would be the best language model?
Well, these are the best ones that exist now. And of course, ultimately, it would depend on what you're trying to do with it. But these ones are very good for many things. You know, so I'm just going to generate text. But it turns out that what people do is you learn on this huge, you know, you feed in all the, you know, I think the thing I'm going to show you was fed in from Reddit, you know, all the Reddit texts ever, which means that it may turn out to be X-rated what we get out. But I decided to take that chance. And so then once it's learned that, it helps it in doing other things. So here would be where you would put translation. You would train this just, you know, in the way we just said, and then you would put in translation, or you would put in question answering, whatever it is over here. And so this part of the model is always, you know, helping everything you do here. But then it depends what you're doing. Like this model, you can use it to answer questions. It produces interesting results, but for a variety of reasons, it's not what anybody. It's not like what Siri or Alexa uses. You know, it's not like a really good question answering thing. For one thing, because you're not quite sure why it works. For another thing, because there is this kind of general idea that a real question answering thing should have a database where it has the actual facts that it's answering, you know, to the questions, you know, and then this doesn't. I mean, it's got it somewhere hidden in all those numbers, but you know, it's so I think the really true answer is there's no very good language model yet. Okay, a really good language model would combine this with something that knows something about what the words mean and about the facts and so forth. You know, and then people are trying to do that, but they haven't really done a good job of that yet. Another question? Yeah.
So how are the values of a vector for each word determined?
How are they determined? Okay, so I went over it a bit fast, and probably a good explanation we should save for, you know, like after, so I can make the demonstration. The basic idea is you have a corpus, and you're going to predict the nearby words. So the task is, given word, predict like maybe all the words, you know, within 3, you know, on both sides. And so you would take the number associated to the word, and you know, the most simple-minded thing would be to say, let's take the vectors which are close to that one, or you can take a dot product and say, you know, the angle should be relatively small. But of course, it has to take other stuff into account. A little simpler thing that, it's a valid thing. It's not what they actually do. You could say, let's try to predict on, or let's try to predict machine. We would take maybe these 6 words, we would take their vectors, we would just add them up, and then whatever is closest to that, those are the ones we predict for this. Okay, so that's the task. That's the rule for if you knew the numbers, what would you do? And then the general way you find the numbers is by this process of training. You say, we're going to measure how well it does on the task. We're going to start with some random numbers. It's going to do terrible on the task. But then we're going to look at every choice it makes and say, well, it got machine wrong. It said, abracadabra. But if I change this number, it would be more likely to say machine. If I change this number, it would be more likely to say machine, and so forth. So let's make little changes to make it more likely to get the right answer. And then let's just do this billions of times. So that's the training. And so gradually it becomes more and more likely to make the right answers. And that's how it comes up with the numbers that it uses. Okay. So now let's see if I can get this other window up here. Okay, so this is GPT-2, which you can download if you have any kind of a computer, but especially if you have one with a GPU. And then this is written in Python, and you can read the code. It's open source. Interactive conditional 345M. So this is using the model to type in a prompt. Okay, I'm going to start it. And then this has already trained all the information of the model. So it takes weeks and weeks using a bank of computers to go through these billion words. Not because billion words take a long time, but because it has to do this training process. And every time it goes through the words, it just gets a little better. And so it goes through these words, the whole billion words, millions of times. Okay, and that's basically the way machine learning works right now. And so that takes weeks. But then they've made the output of this for starting with 345 million words out of the Reddit. They've made the resulting network publicly available, and so I've downloaded it. And they have one with 1 billion words, and they claim they're not giving it to the public because it would be too dangerous. It could produce such convincing fake news, but people are a little skeptical. But in any case, they did release 345 million. And so now I believe we are set. We will try, I guess. So the GPU is working. And so now the idea here is that we type something. We type like 1 or 2 sentences, and then it just continues. So like in the conditional thing, this is P of, here's the stuff we type, and then it just keeps going from there based on the stuff we typed. What's the likely thing? It doesn't always take the most likely. It has a random element. We're just going to take a likely thing, like one out of the top 50 likely things, then one of the top 50 likely things, and so forth. And it will just keep going like that. So, okay. So somebody wants to volunteer to suggest a sentence to type in. How about you? Anybody? Yeah.
Can you try the example used in your slides? So what is the capital of France?
Okay, what is the capital of France? It doesn't care, I don't think, about capital letters, but I did that. Yeah. You're asking about, well, let me do this guy and see what we get. Okay, now it's got to actually start calculating something. So the first time it has to load in this, start at the GPU and load in this TensorFlow stuff. Okay, so there we go. Okay. Okay, what is the world's busiest rail line? Okay, well, okay, why did it go there? I don't know. The Grand Line connects the French city of Chamonix in the Basque Country to the port of Saint-Nazaire near Marseille in western France, forming what has come to be known as the French Empire. When completed, there are expected to be over 30 international passengers traveling over 330,000 miles per day through the part of the line that extends from France's southern port of Yvelines in France to the industrial heart of Libmont in western Germany. Will RTX or France's mass transit system ever be built on French soil? ... Okay, so now you might, the immediate reaction that would have this is it must have just copied this stuff out of articles on the internet. But if you know anything about French geography, you know that nobody wrote that. That is just totally wrong geography. And so then it just goes on. And where it got this railway stuff, I guess it just very early picked randomly, rail line or Grand Line, and then it went running with it. So if I type in the same sentence again, I'm going to get something different. Okay, so let's try it again. What is the capital of France? Except that it's not, well, let's see what it gives. Okay. Well, okay, interesting. So giving it that character has put it in a totally different place. Okay, so I hadn't tried that before, of typing in random characters. Did I? Okay, so I don't need that. Well, interesting. It seems to still be in this slightly different place. Maybe I should restart it. More special edge, especially, okay. Okay, it does better than that. I'm going to try it once more, and if it keeps doing that, I'm going to restart it because I might have put it in some weird mode by typing that open square brace. Okay, directed to the definition of a whole, see note first. The capitals used to characterize French capital are the nation, nice or dark, doing business, inquisitorial or spending, classified by Euro as EU mint, and prospects of North America, law before below light rope. Some definitions. ... Okay, so it's doing something. It obviously got into kind of a legal mode, but now it's wary of alien inflection, class of underfleeces, the third European referendum in the history, the Junkers president motion. Okay, so now it's kind of mas de la decant is excessive. Okay, let's try a different sentence, and then we'll stop, I guess. Who wants to propose another prompt? Yeah.
Does the rats really like cheese?
Does the rats really like cheese? Okay, do the rats really like cheese? Okay. Okay. Okay, amazing video by Wrightscast Games. Can you believe Disney XD, pronounced ignores, tried to remake Pac-Man? It doesn't pile up support further. Its next 5 goddamn theme parks. Tweaked gay people. Okay, so this is what you get from Reddit. Okay, so this one's starting to be maybe a little R-rated here. All images taken by Branty. Comments welcome for selfish reasons being featured on the exceptions reader. Okay, so sometimes it's more on topic than that. Let's see. Okay, let's just try that. Wow. Okay. Z sandwich. By cheese sandwich, I mean something that might look messy and ineffective without them eating plastic bags. Are you really going to believe this? You can arrange them like this. Okay, a little bit of PG-rated stuff there. Okay, the Colonel is using cheese sandwich. So, okay. So, okay, so that's how well I can do. So like I said, so